if I have a hill like this, or as we call it in physics, just to sound smart, an inclined plane, with an angle of, let's say, I don't know, 30 degrees, seems to be the angle we always go with, and then a box with, let's say, a mass of 100 kilograms. No friction, no air resistance, no applied force, nobody's pushing on this or pulling on this. Okay. How do we analyze this problem? Well, we know ultimately this thing is going to go down the hill. It's going to slide down the hill. In the absence of any other forces, it's going to slide down the hill. But why is it going to slide down the hill? What is it that's going to drive it or cause it to slide down this hill? What force or forces are going to cause it to go down the hill? Yeah, good. It's sorry. Okay, good. You said it perfectly. It's F parallel. Let's label F parallel right here. We call this F parallel because this force is parallel to the hill. If it's going to slide down the hill, there's got to be a force that's acting down the hill. But that red F parallel is not a fundamental force. It's not a force in itself, but rather it's kind of a net force. It's kind of a combined force caused by a couple of other things. And Ariel said it herself, the combined forces are the normal force and the force of gravity. Which way does gravity act? Always. Which way does gravity act, Christian? Straight down. So we're going to draw gravity straight down. That force of gravity is m times g, right? And which way does the normal force act? Always. Usually it acts straight up, right? But it always acts, which way? Good. 90 degrees to the ground or to the surface. So in this case, because our surface isn't flat or isn't horizontal, then the normal force is going to act up at an angle like this. Make sure that that normal force is perpendicular to the surface, and make sure that that normal force, when we join the normal force and gravity together with F parallel, make sure the normal force is drawn perpendicular to F parallel. What do we know this angle to be right here? Always. There's a lot of always here, right? That's good. Because if this is always the case and that is always the case, then it should make our questions a lot easier, right? That angle is always going to be not necessarily 30 degrees, but yeah, it's always going to be equal to the one where the 30 degrees is, the angle of the hill right here. All right, so we want to find F parallel, right? Fn and Fg are important. They're important. They're what drive it down the hill, but they combine to give me F parallel. So let's find the value of F parallel. What trig function am I going to use here to find F parallel, given that it's the opposite side and I already have the value? Well, I don't already have the value of the hypotenuse, but I can find it pretty easily. Opposite and hypotenuse are going to give me the trig function. Which one, Nick? Opposite, hypotenuse. Yeah. Sine, right. We're going to say sine, in this case, 30 degrees, is equal to opposite F parallel over the hypotenuse, force of gravity, which is m times g. So F parallel ends up being equal to mg sine 30, or in this case, we're going to say 100 times 9.81. We're dropping the sign of the 9.81 there because we're just dealing with the magnitude right now. The direction is important, okay, but we're not going to worry about the direction right now. We're just going to worry about how big that force is. 100 times 9.81 times sine 30 degrees. And when I solve for that, I think it works out to be 490.5 newtons, which we're going to label right here. The force parallel is 490.5 newtons. Now, if we had a force of friction acting, okay, we add it in, no problem. Maybe somebody is pulling it as well. Maybe somebody's pushing it down the hill. Not only are we having gravity and the normal force pulling it down the hill, but maybe somebody is pushing it down the hill as well. We'll call that Fa. Okay, maybe there's a force of air resistance acting on it. Whatever, it doesn't matter. The F parallel is the hard one. Once we have the value of F parallel, then what do? Regardless of whether we have just F parallel or F parallel and all of these other forces. At this point it becomes easy, right? At this point we just say F net is equal to the sum of the forces, F parallel, which we just found the value of, plus the applied force, if there is one there, plus the force of friction, plus the force of air resistance, if those two forces are there as well. M times A is equal to the sum of the forces, sub in your numbers, and then solve for what you're looking for. Most likely the acceleration, but it could be some other variable there. Does that make sense? All right, let's take a look at our questions. on page 179. Do we have any issues with these questions on page 179? We need to go over one of these or both of these questions on page 179. Okay, let's take a look at number 2 then. It says a 55 kilogram skier is accelerating down a 35-degree slope. The acceleration is 4.41. Okay, this is a good question to go over because we're asked for a different variable than we're usually asked to find, right? Usually it's what is the acceleration? This one's here is the acceleration. What's the force of kinetic friction? Now, let's draw this out. Let's get rid of this one so we can have a little bit more space here. We got a 35-degree slope. By the way, I always draw it like this, just kind of out of habit. Would it be okay if I drew it like this? Would that change anything? No, it wouldn't. Doesn't matter. Hey, I draw like the first one just because of habit, but there's no good reason for that. That's 35 degrees. Our 55 kilogram skier is up here sliding down the slope. There's an acceleration of 4.41 meters per second squared. That's down the hill, right? The skier is accelerating down the hill. So I'm going to make the acceleration negative 4.41 meters per second squared. And we know we must have a force of friction, force of kinetic friction acting up the hill. Agree with that? And if we're sliding down the hill, kinetic friction is going to act up the hill. All right, what other forces do we have acting here? Now comes the part that we repeat every time, right? Hey, Ben, what else we got acting here? Yep, which way does it act? It acts straight. Force of gravity acts straight down, right? Straight down. And that's equal to m times g. What about Fn? Matter G, which way does Fn act? Yeah, 90-degree angle. Right? 90 degree, that is to the surface, like this. So make sure you draw it pretty much 90 degrees there. And we've got to make sure that when we combine those two, F parallel right here is going to be drawn perpendicular to Fn. Let's label this up here. Let's label this as 35 degrees. And now let's find the value of F parallel. Which trig function do we use? Tina, which trig function do we use to find F parallel, given that we're looking for the opposite side and we have the hypotenuse? Good. Sine 35 degrees. This one's a little bit harder to find because it's 30 degrees is easy in our heads, right? 35 degrees, not so much so. Sine 35 is equal to F parallel over gravity, which is the hypotenuse. mg sine 35 degrees. What do we got here? The mass was 55 times 9.81 times sine 35. We get 309.473 newtons. All right, now we can do this. Let's say now F net equals F parallel plus FF. Can anybody explain to me why I'm not taking into account FG and FN? Like I'm saying F net is equal to F parallel plus FF. Where did FG go? Where did gravity go? Where did Fn go? They didn't cancel each other out like they were last week. Yeah? Yeah, I am accounting for FG and Fn. I am in F parallel. Like this is already F parallel and FG. So I've already accounted for those. I've combined them, and then I'm combining that combination with the force of friction. Now the net force is also m times a, as we know. We're going to say m is 55. The acceleration is negative 4.41 because we're accelerating down the hill. F parallel is 309.473. Oops. Plus the force of friction, is that right? Is that right? Not quite. What am I missing here? What's wrong with this? Good. Good. F parallel is negative 309 because we've defined negative as down the hill, right? If we made the acceleration negative down the hill, then F parallel has to be negative down the hill as well. All right, so let's say 55 times negative 4.41. And then we're going to add 309 because it's a negative on the right-hand side, so we take it over by adding, and we get 66.9, which is exactly what they have right here. Positive 66.9, which of course it should be, right? It should be up the hill, so it should be a positive value. All right? Good there? All right, what I'm going to do now is have you work on a few questions on a worksheet. We'll give you some time here in class to work on that. I'm going to ask you to take one of these little packages. There's 4 pages to it. Take one, hand the pile on to the next person, please. And when you get yours, I'd like you to flip to page 3 of this booklet, please, page 3. And then I'd like you to take a look at questions 10 to 13 on page 3 of this booklet. On that page 3, it goes 10 to 14, but I'd like you to look at 10 to 13 on that booklet, please. So look at question number 13. It says calculate the force of friction. This is similar to what we just did as an example here a few minutes ago, except this time we have an additional force acting, which is an applied force up the hill of 80 newtons. So somebody's yanking it up the hill with 80 newtons. There's also a force parallel acting down the hill, and then there's a force of friction. We know that it's moving up the hill because that's what the acceleration is here. If it's moving up the hill, which way is friction going to act? We know this right away. Dylan, if it's moving up the hill, which way does friction act? Down the hill, right. So we know that we're going to draw friction down the hill. I'm going to draw it down the hill. Okay, I'm going to draw right there. The force of friction is down the hill. Okay, just to keep it out of the way, I don't want to get it mixed up with F parallel. I'm going to draw F parallel down the hill as well. But I'm going to resolve some components into F parallel here by drawing the force of gravity, which is straight down, and the normal force, which is drawn at 90 degrees to the boundary. And then F parallel again, we'll draw it again. Remember, it's only one value of it, but we'll just draw it in 2 places here. F parallel is perpendicular to Fn, and then this angle here we have here is 30 degrees. All right, how do you find the value of F parallel? How do we find that value of F parallel? Caitlin? Which trig function do I use to find F parallel? Given that it's opposite, I want to find opposite, and I have the hypotenuse. Good. So let's say sine 30 degrees is equal to opposite F parallel. Somebody, as I was walking around, I saw at least one person call F parallel FP. Is that okay? It doesn't really matter what you call it, right? As long as you understand what you're labeling there. I say F parallel, like 2 parallel lines. You want to say FP, that's fine. F parallel over m times g, so we're going to say F parallel is equal to mg sine 30 degrees, which is 10 times 9.81 times sine 30 degrees, which I believe works out to be 49.05 newtons. All right, good. There we go. 49.05 newtons is my F parallel. Now let's say F net is equal to the sum of the forces. This time there's 3 of them. F parallel plus FF plus FA, the applied force of 80 newtons. F net is m times A. M is 10 kilograms. The acceleration is it positive 1.5 or negative 1.5? Lex is positive or negative? How come it's negative? Am I going down the hill? Let's look at it here. Acceleration is 1.5. So it's a positive value, isn't it? Yeah, it's positive up the hill. F parallel is down the hill. We're going to make that negative 49.05. The force of friction is, well, that's what I'm looking for. We know it's going to act down the hill, but we're not going to put a negative in there right now. Okay, when I solve for this, the mathematics is going to tell me that it's a negative answer. F applied is up the hill, so it's positive 80 newtons. 10 times 1.5 is 15. Negative 49.05 plus 80 gives me 30.95 on the right-hand side, plus FF. Yeah, and take the 30 over by subtracting. 15 minus 30.95, I think gives me 15.95. Negative 15.95. And we want to express it as 2 digits, so negative 16 newtons. Should it be a negative value? Which way did we figure friction was going to be, Max? Down the hill. Does it work out to be down the hill? Yeah, we got a negative value, so it's down the hill. That is, if we made down the hill negative and up the hill as positive, some people may have made it the other way around. If you define down the hill as positive and up the hill as negative, that's okay. But if you did that, you should have gotten positive 16 newtons. Okay? 60 newtons down the hill, whatever sign you assigned to down the hill. All right, what do you think is going to happen if we see a question like number 14? What do you think is going to happen if we see a question like number 14? I don't want to do that question for you right now, but I want to give you a little heads up as to how we might tackle that, okay? So a situation like this. We got an object right here, let's say it has a mass of 10 kilograms. We got an object right here that's hanging over the edge that has a mass of, let's make it 20 kilograms. There's a pulley right here. Remember last week we were doing those pulley problems? Except we're a little bit more straightforward than this because we didn't have that funny angle in there. Let's make our angle 30 degrees here right now. What forces do we have acting on this system? What's pulling on this system? What's causing it to move the 10 kilogram object to either move up the hill or down the hill here? Tell me something. McKenna, what's one force that's acting on this system here? Good. Force of gravity acting on the 10 or the 20? You're right, on both of them actually. The force of gravity acting on the 20, we're just going to call F20. Okay, that makes sense? What's its value? Is it 10 times 9.81, 20 times 9.81, or 30 times 9.81? Leah, which is it? 10, 20, or 30 times 9.81? Sorry? No, not 30 times 9.81. 20, yeah. There is a force of gravity acting on the 10 kilogram object, but we're going to account for that over here, right? Does that make sense? So we're going to account for the other 20 kilogram object over here. 20 times 9.81 gives me 190, what is that? 196.2, I think? 196.2 newtons. Okay, so McKenna said we have a force of gravity acting on the 10. We do. We also have a normal force acting on the 10. We do. And then, of course, we have F parallel right here. F parallel drawn 90 degrees to the normal force. What's this angle right here, Jake? 30 degrees. And then we label F parallel there. I'm not going to go any further with this, okay? Okay, I'm not going to show you any more. Do you see what we're going to do here now, though, guys? Like, once we have F parallel, doesn't this question turn into one of these problems that you had last week that looked like this? Isn't it the same thing? Once you get F parallel? So get F parallel, and you know how to do that because you've been working on that for 20 minutes here today. Get the force of gravity acting on the 20 kilogram object like you would have last week right here, and then combine them. Combine them the way that you did last week. All right, take a look at question number 14 now. See what you can do with it at your desks. All right, let's do question number 14 here. We've got a 5 kilogram object being pulled up a hill. It's also being pulled down the hill by F parallel. And then we got another 5 kilogram object that's being pulled downwards by gravity. Let's label that one first here. I'm going to call this one F5. I usually call the force of gravity acting on an object Fg, but because we've got two forces of gravity here, the force of gravity acting on that one and the force of gravity acting on the other one. I'm just calling it F5 so that I don't get confused. Although, having said that, the other one's a 5 kilogram mass as well, so we could easily get mixed up with that. Anyways, that's what I'm going to call it. We're going to say F5 is 5 times 9.81, which when I do the math will be 49.05 newtons. Now, of course, we also have force of gravity acting down on this one. Now, force of gravity acting down on this one is straight down. I'm going to call that Fg to be consistent, because I always call that one Fg. If I always call it that way, then more likely to remember what to do. Fn is perpendicular there, remember? Fn is perpendicular, and we got to make sure that we draw F parallel, which is the combined force there. We got to make sure that we draw it parallel to the surface, and we also have to make sure it's perpendicular to Fn. So let's get the value of F parallel here. We're going to say, which trig function is it then when you use? Peter, which trig function am I going to use to find F parallel there? Right. So we're going to say sine, I can't see that. Is that 30 degrees? 30 degrees is equal to F parallel. That's the opposite over the hypotenuse, which is force of gravity, m times g. It's mg sine 30 degrees, which is 5 times 9.81 times sine 30 degrees. Gives me a value of 24 point, who's got that? 24.525? Okay, so we got this one now. 24, we'll call that F parallel, 24.525 newtons. Now, as I was walking around and I was kind of looking at what people were doing and answering questions, I saw a number of people make this mistake. A lot of people actually make this mistake. Okay, just about everybody recognized that the next step was to say F net is equal to the sum of the forces, F parallel plus F5, or whatever you call that force of gravity on that second object. And then m times a is equal to F parallel plus F5. M, of course, is 10 kilograms because the entire thing is being accelerated. But here's where the mistake was made. F parallel, we found, was 24.525, and F5 was 49.05. Some people made them both negative. Some people made them both positive. What's wrong with both of those? Making them both negative or both positive. Erica, is your hand up there? I'm sorry? Right here? No, we stick with 10 there because when we're dealing with m times a, the net force on the system, okay, the left side is the system, right? And the net force on the system is dependent upon the total mass of the system. So that's correct. But what's wrong with the 24 and the 49 here? Sarah, do you think you know? Yeah, one of us got to be negative. Okay, lots of people did this. Lots of people made them both negative. Okay, which is just as wrong as making them both positive. I get why people did that, because F parallel is down the hill, F5 is down, right? But if we straighten them out, remember last week I said we like to straighten these questions out? Just pull it out like this, and then we got two objects, a 5 and a 5, with a force this way of 49.05 newtons, and a force this way, F parallel, of 24.525 newtons. Now, tell me what the sign should be. Now it's easy, right? We're going to make the 49 positive, and we're going to make the 24 negative because it's acting to the left in my new diagram. So if you think you might get messed up with those signs, which lots of you did on this question, then just redraw it like I have over here in black on the right-hand side. Okay, so now we got 49 minus 24 divided by 10. I think A works out to be 2.45 or 2.5 meters per second squared. Is that right? Have a look up here for your challenge question, guys. And bear with me on this. I'll explain it, and then you can just snap a photo of this or copy it out, whatever you want to do. We got an angle of 30 degrees, no problem, right? We got an inclined plane or a hill here, no problem, right? No problem. We got a 500 kilogram object on that hill. Whoops. We don't want to do that. We've got we've got another object down here, which is like a 80 kilogram object with a 50 kilogram person inside. All right, that makes it a little bit harder. And then we got a coefficient of static friction, a coefficient of kinetic friction. Ooh, that throws a wrench into things. Okay, we need to be able to find the normal force, but you can do that, right? If you could find, I don't know why it wants to do that on me. There we go. If we can do Fg and Fn like this, and F parallel like this, we can find the value of Fn, right? We're going to need the normal force to deal with the coefficient of friction. So here's what happens. The system is released. It's allowed to do what it does. Okay? If it overcomes static friction, then it's going to move. And if it doesn't, then it's not going to move. But regardless of what happens, 4 seconds after it's released, so 4 seconds after I let this thing go and do what it does, the man throws the ball at an angle of 30 degrees from the horizontal at a speed of 20 meters per second. Your question is, how far does the ball go? Where does the ball land right here? What's this distance? Right. Boy, oh boy, oh boy. That looks like a challenge question if I ever saw one. We should make this question our final exam question, eh? Like it's like, or, oh, I got it, a unit test question. The unit test question. This could be your unit test because it pretty much takes care of everything we've done this unit just about, right? Inclined planes, there's an elevator. Oh, there's even projectile motion from our last unit. All kinds of crazy stuff here, right? Let me scroll down here a little bit so you can see the whole question. Now you can snap a photo of it or do whatever you want to do so that you've got it and take a look at it.